Hello guys, in today's video we are going to talk about a classic dynamic programming problem named the knapsack problem. In this problem we are getting an array that includes n items with their value and weight. We are also getting a knapsack with a limited capacity. The goal is to fill the knapsack with a set of items that has the highest possible value without exceeding the given capacity limit. But before getting into the action, let's match our expectations. I'm studying this topic by myself, and my videos depend on the wisdom of the crowd, a topic that really fascinates me. Therefore, if you find any mistake in what I say, please let me know in the comment section below. I promise to read all comments and re-upload if necessary. Also, please subscribe to my channel. I upload many videos on this topic. The naive solution to this problem is to compare all 2 to the power of n subsets of items. Since for each of the n items there are 2 states, either the item is on the set or not. For each subset to check if it does not exceed the capacity limit, and if indeed it does not, comparing it to all other qualified arrangements. This solution would use O2 to the power of n space, and its runtime is exponential too. A better solution involves a recursion that decreases the input we work with in terms of capacity and selection of items. Let's see it. Alrighty, the knapsack problem. Given an array of items with their value and weight and the capacity limit, the knapsack, we want to return the subset with the highest value that does not exceed the capacity limit. Let L be our capacity limit, let J be our selection of items, let Wj be the weight, and Vj be the value of an item we are currently reviewing. The recursive function f for our problem is the following: f of Jl when J is the number of items in our selection, and L the capacity limit, which equals to 3 scenarios, the red one. If we no longer have any items to choose from, we are simply returning 0. The second scenario is the pink one, when the weight of the item exceeds the capacity of our knapsack. The third scenario is when we can choose the item, but it is not necessarily worth to us to choose it. And as you can see, the red line represents the base case. There are no more items to choose from, and we return. The pink line represents the item exceeds alone the capacity limit, hence we cannot select it, and we make a new recursive call to function f without it. And the yellow line is called when we can choose to add the item in question to our set. We are making 2 recursive calls, one without the item, identical to the pink line. The second call represents we added the item, reduced its weight from our capacity limit, and added its value to our take. When we return, we would move forward with the option that gave us a better result. To implement our algorithm, we need to fill a table with n rows and l columns to accommodate all valid arrangements. Therefore, the running time is O n multiplied by L. The memory space required is also O n multiplied by L to store our table. We need to prove that the return value of our recursive call fjl indeed returns the most valuable subset that does not exceed the capacity limit L. To prove that claim, we need to prove, first, that it is possible to find a subset whose value is fjl from a set that has the item 1, 2, 3 all the way to j with capacity limit of L, and secondly, that it is impossible to build a subset whose value is more than fjl under the capacity limit L. Both claims can be proved with induction on J. This problem has a second version, called the greedy version, when you can take part of an item. In that case, we would always look for the item that offers the best value to weight ratio, and take as much as we can from it, until we exhausted the item resource or capped our weight capacity L. This version is reasonably easier. Well, that's about it. I hope you learned something new from this video, and please comment below with your thoughts. First degree studies in university are all about social studies, and this project comes to encourage that. even through complicated situations most of us are going through right now. Thank you so much for joining me. Please subscribe to my channel. Until next time, good luck.